Oh, good afternoon. So I am going to finish up the balance of the lecture that I started this morning. I didn't quite get a chance to finish it. So I put a completion slide in here. Let's see here then. So where I started, or where I ended off, and I just wanted to go back over this slide a little bit differently. So we spent a lot of time talking about the Google Spanner and the approach that it took. And it incorporated an awful lot of the different techniques we've been talking about into the way that it actually implemented its system. But there are other mechanisms that are available to us and are in use by others. I started talking about snapshot isolation this morning. I thought I'd go back and touch on this a little bit more. This is a different approach. So when we do snapshots, we can do like whole snapshots of the entire database. But this is looking for something more nuanced than that, where actually what we want to do is we want to be able to snapshot individual changes. So if we think about it, we can logically think, and I did make this point this morning, which is we have lots and lots of records in our database, and only a few of them actually mutate as we move from transaction to transaction to transaction. It's just the nature of this kind of work. So yes, we can construct models where everything changes every single time, but that's not really of interest here. The much more common case, and the one that we're interested in, and the reason we're going to talk about snapshot isolation, is because we may be just changing a few of these records. So how do we actually do this? Well, I've talked about using two-phase locking and two-phase commit, and these two things tend to tie together pretty closely. Well, a different way of doing this is to relax things and to say we just need to make sure that we do things in a consistent fashion, but it doesn't necessarily have to be. Uh, so we just need to know what the ordering of events were. One of the things that I haven't I have talked a little bit about this, but one of the things that you can do is you can actually encode things as operations instead of data changes. Data changes make this kind of work where you have multi-versions, for instance, a little well, it makes it a lot more difficult to reason about. There's paper that I actually really like. I call it an abandoned paper because it was published at the Symposium on Operating Systems Principles, which in systems is kind of the top tier conference. Um, and it was actually presented at the same time that Dave Gifford presented his quorum replication protocol. So they were very much concerned about these issues. And I've already talked about quorum replication, and we'll talk more about it because it's really important. But in this case, they called it polyvalues, which was the idea that, we don't really have to lock people out of the transaction if it's possible for us to compose their operations in a way that allows us to correctly recover in case one of the transactions fails. So, for example, I have 10 books in inventory. You take a book, you put it into your cart. I now reserve one of those, so I now have 9. You've got a transaction against that. I don't have to block everybody else out from buying the next 9 books. The order in which it gets decremented, I don't actually care very much about. So the idea is that what you can actually do is you can keep different versions of things and essentially keep multiple values depending on which transactions roll forward. I've mentioned MRDTs, which are a kind of replicated data structure. They were proposed just a couple of years ago, and they are a formalization of exactly this technique about how you can have multiple versions that, provided that your operators obey particular principles, you can actually compose these operations together, and that really loosens your need to serialize. So what we're looking at is we're trying to relax serializability, or at least relax it enough so that we can have some additional parallelism and still reason about what the actual outcome was if we have to roll back some transactions. I haven't decided yet, but I have been thinking about doing a lecture later in the course. I've got a number of slots there for interesting topics that I can talk about. And I have considered talking about CRDTs and MRDTs because they are very interesting data structure level distributed system elements that can be used for building some very high performance kinds of distributed databases, for instance. So at any rate, what I'm talking about now is what can we do to allow this kind of parallelism. So we allow concurrent activity that doesn't compromise our ability to recover. It does make it more difficult for us to reason about, but it provides, in exchange, it provides a much better performance model than only one thing through at a time, which works pretty well. And if you've got a lot of independence of data, then that's fine. Sometimes this kind of snapshot isolation could even be combined if you had hotspots, if you had small pieces of the database that had high concurrent access. In most cases, when you don't have a lot of access to the same object, you don't really need to have this kind of additional complexity. It's not justified. So what is the correctness that we're guaranteeing here? Well, the transactions do actually read from some version of the distributed state. And it may not be the most recent. And this is why we're kind of relaxing that. Well, no, it's not even kind of. We are relaxing the serializability of the overall system, even though we can still reason about what the final outcome is at the time we have to make it consistent. So our sequence of snapshots is in fact serializable. In other words, there can't be circular dependencies. This transaction can't depend on the second transaction, which depends on the first transaction. That doesn't work. Those kinds of cyclic dependencies have to be blocked out or merged. Those, you don't have any other choice because they're dependent. So you have to have a system that is acyclic. So one of the first one I'm going to talk about is example of a system that uses a different model is Amazon Aurora. AWS Aurora was described by in a paper published in 2015 at SIGMOD, the Special Interest Group on I don't even remember what mod is, but it's about databases. And it's one of the two big database conferences. So this was a primary backup model. I don't know why I made backups plural. Actually, no, I do know I made backups plural. It is a primary backups model because you have one primary and multiple backups. I did actually make that. I did that deliberately. Now I remember. So it is high availability. We have two nodes in a single zone. Think of a zone here as being a data center. And then we have at least 3 zones. So we have replication across 3 different locations. And of course, 3 is a magic number that we'll see over and over again because as I was talking about earlier today, that's what gives us this guarantee that we can reach quorum. So as long as we have 2 of those 3 nodes, we can reach a consensus between us as to what the outcome was. We can recover back to a consistent state. This does actually use a quorum replication model. I've mentioned this. I haven't gone through it in detail yet. I will go through it in detail a little bit later. It is this, from a high level perspective, it's the idea that we have multiple different sites and they each get to vote on what the outcome is. And in essence, as a client, yes, as a client, as the thing that's talking to the multiple replicas, the way that I guarantee that I have quorum is that I talk to some number of them that guarantees that quorum. The simplest model is where every node in the system has one vote. And so all I need is n plus 1 over 2. I just need to have a majority vote. There are actually models that we can use that will allow us to reason about less than majority quorums. I'm not going to get into that right now. I'm going to save that for a later time. The downside to this model is that, in fact, having 6 copies of everything, because we've got 2 nodes in a zone, 3 zones, that's 6 copies, that's a lot of I/O amplification. For every change that I make, I'm writing it 6 times. Whoa, that's a lot of extra I/O. Yes, I get to parallelize this I/O, so in fact it might not actually increase the latency significantly, but it still is a lot of extra I/O, and so that is a downside to this particular architecture. So let's compare AWS has both a MySQL product and this Aurora database. And in essence, they built Aurora because they wanted something that was more scalable and better than MySQL. Whether or not it was because they didn't really like Oracle owning MySQL or not, who knows? At any rate, um, so Amazon offers both. You can choose either one. When you use MySQL, what Amazon does is they actually do primary backup and they put them on top of Amazon services. Amazon Elastic Block Store, Amazon S3, which we talked about in today's failure, and a mirror for the Elastic Block Store. So basically, we have a couple of different tiers in a storage layer. We're mirroring things so that protects us against the failure of any one of those EBS instances. So we've got a lot of redundancy built into this, and its biggest cost is that, of course, we have to do all of this replication of the data between the primary and any replicas. And this does support multiple replicas. In essence, if you look at this, this looks an awful lot like Project 3. When we look at how they structure things in Aurora, Aurora has one primary instance and two replica instances, so 3 total instances here. And then each of those are in turn mirrored in S3. So they've eliminated the need to have the Elastic Block Store in the middle. As long as they have more than half, in this case it's 4, because it's n plus 1 over 2 and round up. So it's six total copies, 6 plus 1, 7, divide by 2, 3.5, round up to 4. So you have to have at least 4 of the copies must have a copy of the of any changes. So Amazon's report on this was, look, we did this. It's actually very performant. It runs really fast. It gives us strong recoverability. We have high availability, and that was really their concern. And they had good performance with it as well. As I recall, it was actually quite a bit better than the MySQL case. And that was really it. That was just just those samples. So I almost made it finished in time. So what are we talking about in today's lecture? We talked about different techniques for distributed transactions. I'm not saying that one of them is better than any other. I'm saying that these all have trade-offs and they are all making decisions that are specific to a particular workload. We talked about Spanner, where Spanner uses Paxos, it uses two-phase commit, it uses two-phase locking, and it has true time. I'm going to talk more about Paxos in a future lecture. Paxos is a big topic, and it achieves consensus and it uses some of the ideas we're talking about here, but it does it in a way that eliminates the leader as a point of failure. If you start looking at Project 3, you will notice that the view server is a single point of failure. It's not a good design from that perspective. It's not a good design from a distributed systems perspective because you never want a single point of failure. It's there because it's a convenient way of getting you used to this kind of dynamic change that we're going to have to deal with when we get into Paxos. Once we get to Paxos, then we're going to have to worry about this in a very different way. Because in Paxos, what we're going to do is we're going to be electing a leader. We're going to have someone who plays the role of coordinator, and that person can fail. And then what happens is we go back as a group and we elect someone else to run to be the leader. When the leader comes back, then they find out they're not leader anymore, and they then have to rejoin, and that means that they have to go through any resync to make sure. Why do we do that? Well, we do Paxos because it gives us no single point of failure. It gets rid of that leader that might go away, which we clearly don't want. So I also talked about these other systems where we're using things like optimistic concurrency control and snapshot isolation and multi-version concurrency control. I didn't really talk about it, but it is there as well. This idea of log replication. I've talked about logs before. If you think of it, really all a log does is it already creates a serialized version of events. So if you replicate that log across the different copies, in order to restore consistency, you just have to replay the log. Everybody just has to agree at what point you're going to play the log up to. So when we do recovery, log replication is really powerful because when we do recovery, or even when we're trying to resync our state, it gives us a point where we start. We say, oh, look, I can start right here in the log because that's the last log, that's the first transaction I haven't seen. And then I just play the log forward. Or maybe if I'm doing an undo log, then I might go to a later transaction and roll it backwards. But either way, it's easy to recover. It's easy to reason about. And when people look at logs, they automatically have an ordering of events. So we've already solved, in essence, we've already solved the clock problem because someone has defined the order of events within the system. So that's it for this completion lecture. I know it wasn't too long. Hopefully it wasn't too complicated. There's a lot of meat here, a lot in distributed transactions, and hopefully you found this useful. I'll see you next week. Now I just have to find OBS Studio and shut things down. All right, well done. Have a great day.